Hello everyone, welcome back to another video. Today we are going to be looking at the laminar flow of this cylindrical pipe right here and how the fanning friction factor relates to that. So basically what's going to be happening is we are going to have this pipe that is going to be filled with fluid, and we are going to have this control volume right here. This is the cylinder within the cylinder right here. And pretty much what's going to be happening is there's going to be a change in altitude from the top to the bottom, right? And the first step that we are going to be doing is we are going to be doing a force balance of the pipe right here. So first of all, we are going to have, we're going to be looking at two different locations on this pipe. We're going to have position 1 up here at the top. We're going to have position 2 down here at the bottom. And this length up here, this height, going from the bottom of the pipe to the top of that pipe is going to be delta Z, otherwise known as our change in altitude. Now the forces that are going to be acting on this pipe is going to be a force of gravity pushing down on it, right? And then we are going to have a stress force pushing up. And those are going to be our two forces that are going to be acting on the pipe. And for this Fg right here, we're going to go ahead and dive on into our force balance. This Fg is just going to be the density of the fluid within this pipe multiplied by the volume of the pipe multiplied by the acceleration due to gravity. So we'll go ahead and write that out. That is going to be our expression for the force of gravity. And up here, as we know, this volume, that is just going to be the volume of this pipe right here. So that is going to be pi r squared multiplied by the height, which we said this height is this delta Z expression over here, the change in altitude. So the volume right here is just going to be pi r squared delta Z. So we can go ahead and substitute that in for V. So this is going to be the density of the fluid times pi r squared. This is going to be little r for now. We're going to say that little r is going to be the radius right here of our inner cylinder, our control volume right here. And then we are going to say that we're going to use big R to represent the radius of the full pipe. All right, so this is going to be little r squared right here. And then next step, we're going to find an expression for our stress force right here. And that is just going to be our shear stress multiplied by the contact area. So we'll go ahead and write that out. All right, we'll go ahead and use this symbol right here to represent our shear stress. And next, we're going to have to figure out what our contact area is. And that is pretty much just going to be 2 pi r times the delta Z right here. So we'll go ahead and multiply that by 2 pi r multiplied by delta Z. All right, just realized up here we forgot to multiply this by our delta Z and our G again. So again, this pi r squared delta Z is the volume of the pipe, and once again, we forgot our acceleration due to gravity. We need that. That is important. Got to make sure you're including that. And so now pretty much what we're going to do is we're going to say that the addition of our force, our stress force, and our force due to gravity, that is going to combine to equal 0, because this is a balanced force equation right here. There's no net force acting on it. So that we know adding them together is going to be equal to 0. So we're going to say that Fg plus Fs is equal to 0. Then we'll go ahead and substitute this in for Fs, and we'll substitute this in for Fg right here. And then we'll go ahead and cancel some things out. There we go. And now if we take a look at this, we can see that our changes in altitude are going to cancel out, and our pi's are going to cancel out, And it looks like we have an r over here that's going to cancel with this exponent right here. And so our new expression is just simply going to be density Rg, and then this is going to be, oh yeah, that's right, we forgot our shear stress expression right here. So we'll put that in. That is going to be plus 2 shear stress, like so. And then this is going to be equal to 0 right here, all right? Okay, so our next step is going to be looking at our shear stress expression over here. And we know that shear stress is going to be equal to the viscosity multiplied by the shear rate. So we can go ahead and write that expression down over here. We'll just go ahead and make room over here. We're going to use mu right here to represent our viscosity. And then we know that shear rate is going to be equal to the differential change in the velocity over the differential change in the radius. So we'll go ahead and say this is equal to dV dr. And then we can go ahead and substitute this down here for our shear stress expression right here. All right, next step is we are going to want to isolate dV to one side and put everything else onto the other side in order to integrate. So we'll go ahead and do that now. We'll go ahead and subtract this side over to here and then divide it by 2 mu and then multiply by dr. So we'll go ahead and do that. All right, we brought this r out because we are going to be integrating with respect to the radius. So now we'll go ahead and integrate. And again, we can bring this out of our integral because that is just a constant. That's not going to be changing, so we don't need to integrate that. There we go. And then this side is just going to become v. And then this side over here is going to become 1/2 r squared right here. And then this is also going to have a plus c at the end because it's an indefinite integral. So we are going to need a constant of integration, which we are going to solve for later. So this is going to become 1/2 r squared right here. So we'll go r squared over 2 plus c. Then we can go ahead and erase all this stuff up here, clear up some room. Alright, so now we are going to need to solve this expression right here at a certain point in order to solve for our constant right here. And we know that when our radius over here, the radius of this sample volume right here, when that little r is all the way out to our big R over here, meaning that it is the full radius of the pipe, we know that the velocity is going to be equal to 0 due to the no-slip boundary condition, right? Out here by the very edge of the pipe where the pipe is not moving, we know the velocity of the fluid is not going to be moving either due to the no-slip boundary condition. So we can solve this right here for when r equals r. We know that v is going to be equal to 0. And then we can go ahead and solve for c using this. So we're going to substitute big R in for r, and we know that v is going to be 0. So we'll go ahead and write that out. 0 is equal to negative rho g big R squared over 4 mu plus c. And then all we really have to do is we can add this expression to both sides, and that is going to give us our expression for c right here. So C is going to be equal to rho G big R squared over 4 mu. And there you go. We can substitute that in down here for our constant of integration, and that is going to give us our expression for our velocity down here. So we'll go ahead and write that out. All right, there's going to be our expression with our C substituted in. And the next thing we can see that is pretty obvious is we can go ahead and factor out our density times acceleration due to gravity over 4 mu. And that is going to leave us with an r squared minus little r squared in parentheses. So we'll go ahead and factor that expression out. That's going to be big R squared minus little r squared. There we go. Go ahead and erase down here. Okay, so our next step is we are going to be bringing in a flow into our expression. And we know that flow is just going to be equal to the velocity multiplied by the area. So we can say that Q, which is our flow, equals VA. And we know that we can say that this is also going to be equal to a velocity, an integral of velocity multiplied by a differential area. So we can say that this is going to be equal to V dA. And right here, this dA, we can say that this is going to be, this differential area is going to be a differential radius of different shells, infinitely many different radiuses going all the way out to the complete pipe. So we can put this in terms of dr, and this would turn into V multiplied by 2 pi r dr, 2 pi r being the circumference at a given radius. So we'll go ahead and write that out. And this integral is going to be going from 0 all the way out to big R. So we are going to start out with a small radius of 0. We're going to calculate that out, and then we're going to do a radius, infinitely many radiuses, all the way from 0, expanding all the way out to the outer perimeter of our cylinder over here, which is a radius of big R. So this is going to be our bounds of integration right here. And the next step we are going to do is we are going to go ahead and we already have our expression for V right here. So we can go ahead and substitute that in down here. So this is going to become the integral from 0 to R. We'll go ahead and write this out. Substituting in this expression for V down here. And we still have this 2 pi r and then dr. All right, and we can go ahead and factor out a lot of these terms outside of our integral right here. So we can substitute out this rho g over 4 mu, as well as our 2 pi right here. That can come out of our integral. And basically all that would be left with is we would factor this little r out into this r squared, big R squared minus R squared term right here. So we can go ahead and write that out. And this 2 and 4 will also cancel out, just leaving a 1 over 2. So we're not going to need the 2 at the top there. So it's going to be pi density gravity over 2 mu right here. Then we have our integral from 0 to r. And And then this little r is going to be factored out. That's going to give us big R squared multiplied by R minus R cubed. This is going to be a differential radius right here, so we can go ahead and erase a lot of this, give ourselves some space, and start back up at the top. Alrighty. So our next step is simply going to be integrating this out and then plugging in our bounds of integration. So this term right here, this r is going to be going to an r squared, and then this is going to be getting divided by 2 right here. And then over here, this r cubed is going to become r to the 4th, and that is going to be divided by 4. So that is going to be our solved integral right there. So this is going to become r squared times little r squared over 2 minus r to the 4th over 4. And then this is going to be getting solved from 0 to r. There we go. And as you can see here, when we plug in our bounds of integration, we're not going to really have to worry about our lower bounds, because if we plug in 0 for our little r, this is going to become 0, and this is going to become 0, and it's all going to be 0, so we're not even going to have to worry about that. We're only going to be plugging in our upper bound over here, our big R, and then when we get that, this little r squared has become a big R squared, which is going to be getting multiplied by another big R squared. So this is going to become r to the 4th, big R to the 4th over 4. And then plugging in big R for little r, this is going to be big R to the 4th over 4. So pretty much what this is going to become is big R to the 4th over 2 minus big R to the 4th over 4. And pretty much what this can just be thought of as 1 over 2 minus 1 over 4, which we know is just going to be 1 over 4. So we can just say that this is going to be r to the 4th over 2, or over 4, excuse me. So we can go ahead and write that out. So q is going to be equal to this term right here multiplied by r to the 4th over 4. There we go. This is going to be our expression for the flow rate right here. And our next step is just going to be pretty much, I guess we can go ahead and multiply our 2 by 4 just to make this a little simpler. Make this an 8, just so it looks a little better. There we go. And another step that we can do to simplify this is we can put this in terms of a diameter. So we know that diameter over 2 is going to be equal to r. Diameter over 2 is equal to r. This is supposed to be a d right here. Kind of looks like an O. Let's make sure we know this is diameter. And this is an r over here. And what's going to happen when you take both sides to the 4th, this is going to become d to the 4th. I believe 2 to the 4th power is going to be 16. So this is going to become d over 16 that we would substitute in for here. So we'll go d to the 4th over 16 is going to be getting substituted in for our r right there. And that is pretty much going to turn this into d to the 4th. And then we'll have 8 times 16 at the bottom down here, which is going to be 128. Quick math. So this is going to be 128. And this is going to become our diameter to the 4th. And this is to the 4th. Here we go. This is our expression for our flow over here. And we're going to go ahead and get into our Bernoulli's equation. Okay, so I've gone ahead and written down the Bernoulli's equation right here, and the reason I have done this is because the end goal for this problem is going to be to show that the fanning friction factor right here is going to be equal to 16 over the Reynolds number for this laminar flow right here, all right? And in order to get that, we're going to have to bring in this Bernoulli's equation, so we'll go ahead and take a look at this now. And the first thing we're going to do is we're going to cancel out some of these expressions over here. So if we take a look over here, we have the pressures right here, and we know that the pressure is going to be constant throughout this whole problem, right? It's going to be 1 atmosphere always and forever. No matter where you're at in this pipe, it's always going to be 1 atmosphere. So we can go ahead and cancel out this expression. And we know that the velocity of the fluid within the pipe is not going to be changing either. That's going to be remain constant. So we can go ahead and cancel this out. And we are just left with our acceleration due to gravity multiplied by the change in altitude is going to be equal to the negative frictional heating right here. This is our expression for the frictional heating. So we can go ahead and just erase all this over here. Alright, so now we have our expression over here. The acceleration due to gravity multiplied by the change in altitude is going to be equal to our negative frictional heating right here. And what we're going to go ahead and do now is we're going to do some algebra over here to get G isolated and get an expression for G that we can substitute in down here. So we'll just go ahead and do some algebra right now. So we're going to get G is equal to Q. We'll throw the 128 all the way at the edge right here. Q mu, and that is going to be over let's see here, pi density and then d to the fourth. All right, this is going to be our expression for G right here that we would go ahead and substitute in for G. And now we're going to need to come up with an expression for our fanning friction factor over here. And we know that that is going to be equal to 4 times the fanning friction factor, and that is going to be multiplied by our change in height over here over the diameter, and that is going to be multiplied by the velocity squared over 2. So we can go ahead and get our expression in for that. Tried my best to do the fancy F on the fly, didn't work out too well. 4 times our fanning friction factor, and that is going to be multiplied by our change in altitude, which we can go ahead and just write as our delta Z, because it's going to be the same thing as the delta Z for our pipe that we used earlier. And then this is going to be over the diameter, and then this is also going to be getting multiplied by the velocity of the fluid squared over 2. All right, so this is our expression for our frictional heating right here, and we can go ahead and do substitute this in over here, and we'll go ahead and substitute in our G at the same time. So we're going to get 128 Q mu, bring our delta Z in, over pi density diameter to the fourth. And over here we can say that this negative is going to go away because this is in terms of a change in altitude, and over here our initial position is going to be up top, and then we are decreasing in height going down. So we could say that this delta Z would also be negative, and since there's going to be a negative over here and a negative over here, those negatives would cancel out and both sides would become positive. So we'll go ahead and write out our right side over here, 4F delta Z V squared all over 2D. And now we're going to go ahead and cancel some things. Our delta Z's are going to cancel over here. This D to the fourth would become D to the third and cancel out with this D right here. All right, and then we have this 4 over 2 would simply become 2, which we would divide over to the other side and get 64 on this other side. So this 128 would become 64. All right, let's see. Is there anything else we can go ahead and cancel out at the moment? I'm not seeing anything, so we'll go ahead and write out our more simplified term right now. 64 q mu pi density d to the third is going to be equal to f v squared. Actually, we can just put f v squared since there's going to be no denominator. All right. All right, so the next step that we can make is we can go ahead and multiply both sides by the velocity squared because we want to get f over here by itself, because once again we are trying to prove that f is going to be equal to 16 over the Reynolds number. So we'll go ahead and divide both sides by v squared. That'll cancel out with that side, and then we would get a v squared in the denominator over here. All right, and the next thing that we can do is we're going to bring our flow equation back into this. All right, so we know, well, first of all, let's talk about this Reynolds number up here, all right? So we have this Reynolds number, all right, and we know that this is going to be equal to the density of the fluid multiplied by the volume multiplied by the diameter over mu, all right? And I think I said volume, I meant to say velocity, all right? So this is going to be equal to density times velocity times diameter, all right? And then this is all going to be over mu, our viscosity. So this is what we are trying to get right here, all right? So what we're going to do next is we're going to bring our flow equation back into it. And if you remember earlier in the video, we said that flow was equal to the velocity of the fluid multiplied by the area. And another way that we can express the area is pi d squared over 4. So we can go ahead and say that Q is going to be equal to V pi d squared over 4. All right, and then this would also be multiplied by v. Can't forget about the velocity over here. So this is going to be v. All right, and then we can go ahead and substitute this down in here for q. And that would get these pi's to cancel out. And then we would get a v canceling out. This would turn this into just a regular v to the 1. Then we'd have a d squared over here. That would cancel out this exponent, getting this to be just a d. And then this 4, we can divide that from the 64. That would give us a 16 up top. So this would turn into 16. All right, that's all of our factors over here accounted for. So now we can go ahead and write out our new fanning friction factor. This is going to be 16 q times viscosity all over the density multiplied by the diameter multiplied by the volume. All right. And yeah, I guess we don't need the Q anymore since we substituted that in already, so we don't need that. So this would just be 16 multiplied by the viscosity up top. And as you can see here, if we had Reynolds number to the -1, which is what it is right here, we would have mu over this density, velocity, diameter expression. So as you can see here, that this is going to be equal to 16 over our Reynolds number. So this is our final solution right here. This is showing that the fanning friction factor is going to be equal to 16 over the Reynolds number for this laminar flow through this pipe over here relating to the change in altitude. And that is going to do it for today's video. I hope you all enjoyed. Subscribe if you want to see more content similar to this, and smash that like button if you enjoyed the video. And yeah, have a good one.